Today we will see two very important concepts: the concept of linear combination and concept of linear dependence and linear independence. Those are very important concepts, so we need to focus on them. They are not complicated, but we need to learn them and assimilate the material. Those concepts are applied to vectors in general, vectors in Rn, so columns of real numbers. They can also be applied to matrices, functions, different types of functions, polynomials. So it's very general, but for us, we will focus on vectors in Rn, so columns of real numbers. That's what we are going to see here. And that will be the only thing that we are interested in the course. So the linear combination, we first need to see what is the definition. So here the vector W is called linear combination of vectors v1, v2, vk, if and only if there exists scalars, so the numbers, constants, c1, c2, ck, such that the vector W can be written as a summation here. So c1 times v1 plus c2 times v2 plus c3 times v3 plus ck times vk. So if we can write W as a linear combination here, that this is what is linear combination, the meaning of it. It is a number times a vector plus a number times a vector plus a number times a vector. So if we can do this, then W is a linear combination of vectors v1, v2, v3, vk. And the numbers c1, c2, ck, they are called coefficients of linear combination. So our goal is to see if we can find those numbers. If we are given vector W and vectors v1, v2, vk, we want to see if we can find the coefficients of linear combination. So we start with a simple case. We have here vectors in R2, E1 and E2, vector 1, 0 and 0, 1. Those two vectors form a standard basis for R2, and all vectors in R2 are actually linear combination of E1 and E2. For instance, vector minus 4, 2 is actually minus 4 times E1 plus 2 times E2. So very simple. So vector minus 4, 2, so vector W is a linear combination of vectors E1 and E2. The same thing here when we have another vector in R2, 5 pi and radical 7. Well, we have here that vector written as a linear combination of vectors E1 and E2. So linear combination is a very simple thing. It's some number times a vector plus a number times a vector. So that's what it is, linear combination. Nothing special. So every vector in R2 is actually a linear combination of these standard basis vectors E1 and E2. In R3, we have three vectors that form a standard basis: 1, 0, 0, 0, 1, 0, and 0, 0, 1. For instance, vector W here, 2, 5, minus 4, is a linear combination of vectors E1, E2, E3 from R3. Simply written like this: 2 times the first vector plus 5 times the second minus 4 times the third vector. So this vector here, W, is a linear combination of vectors E1, E2, E3 from R3. Again, linear combination is just a number times a vector plus a number times a vector plus a number times a vector. The question that we are going to ask most of the time is, given a vector W and given vectors v1, v2, vk, what we want to know is vector W a linear combination of vectors v1, v2, v3, vk? And the answer is yes or no, depending if we can find these scalars c1, c2. So another way of asking the same question based on the definition is, Do there exist scalars C1, C2, Ck such that vector W can be expressed as this summation here? So this is a linear combination. So can we write W as a linear combination of V1, V2, V3, Vk? But that will depend if we can find the scalars C1, C2, C3, Ck. If they exist, then the answer is yes, W is a linear combination of vectors V1, V2, V3, Vk. If scalars C1, C2, Ck do not exist, then W is not a linear combination. So it's very simple. In the case of two vectors, so that's easy to figure out what's going on. Well, two vectors W and V. W is a linear combination of vector V if and only if there exists a constant C such that C times V is equal to W. So basically, W is a linear combination of V if and only if W is a scalar multiple of V. Scalar multiple means some number times V. Obviously, if C is different from 0, then we have a very interesting result. If W is a scalar multiple of V, V is also a scalar multiple of W. So here, when W is a linear combination of V, then V is also a linear combination of W. Obviously, W cannot be 0 and C cannot be 0. So what happens actually with vector 0? So this is curious. Well, vector 0, by definition, is any vector times number 0. So vector 0 is actually a linear combination of any vector in Rn. Very simple. However, we cannot find a vector W other than 0 itself that is linear combination of vector 0. But obviously, if I take vector 0 and I multiply it by any number, all I get is a vector 0. So vector 0 is a linear combination of any vector, because we can multiply by 0 always, number 0, but we cannot get any other vector from vector 0. So that's just an observation. So vector 0 is a linear combination of any other vector. So here we have three vectors, W, V, and U, and we want to know who is linear combination of whom. So clearly we can see that W is negative 2 times V, because if we multiply V by negative 2 we get W. So obviously W is a linear combination of V, because we have a number times V equal to W. So W is a linear combination of V. And obviously we can rewrite the equation this way. So now we can say V is also a linear combination of W, because we have a constant times W equal to V. So in this case, V is linear combination of W and W is linear combination of V. When we check vectors V and U, well, we see that we cannot multiply U by any number to get V. If I try to multiply U by any constant, I cannot get V. Because if I multiply, let's say, by 2, I'll get 2, 2, 2. I'm not going to get 2, 1, minus 4. If I multiply by minus 4, I get minus 4, minus 4, minus 4, which is different from 2, 1, minus 4, obviously. So I cannot find a constant C that multiplies U, that multiplies V to get U, or to multiplies U to get V. In this case, we know that U is not a linear combination of V, and V is not a linear combination of U, because I simply cannot find a constant to multiply one of the guys to get the other. In the case of V and W, I was able to find a constant that multiplies one guy to get the other, here also. So in that case, V and W were linear combination of each other. But in case of V and U, such a constant does not exist, so V is not a linear combination of U and U is not a linear combination of V. If we have three vectors or more, So W and then V1, V2, Vk. What we want to see is W a linear combination of these vectors here, V1, V2, Vk? Well, we need to solve this system, obviously, by definition. This is the definition. We want to see if the scalars C1, C2, C3, Ck exist. So we need to solve the system. Well, this happens to be non-homogeneous system, where the unknowns are C1, C2, C3, Ck. So how do we solve non-homogeneous systems? Well, we apply elementary row operations and Gauss-Jordan method. So that's what we are going to do. So if a system has at least one solution, then we can say that W is a linear combination of vectors V1, V2, Vk, obviously. And if the system does not have a solution, that means somewhere in the process we have a contradiction, so the system doesn't have a solution, so constants C1, C2, Ck do not exist. Therefore, W is not a linear combination of C1, C2, V1, V2, Vk. So our unknowns are the constant C, C1, C2, Ck, and we are trying to find them by solving the non-homogeneous equation. If we have a solution, then we say W is a linear combination of vectors V1, V2, Vk. If we do not have a solution, then we say W is not a linear combination of the vectors V1, 2, Vk. So an example here, we have W and U and V. So the question is W a linear combination of U and V? Well, by definition, what does that mean? Well, it means that we need to find coefficients C1 and C2 such that this equation is satisfied. So do we have coefficients C1 and C2 such that this equation is satisfied? Well, we need to solve the system in order to answer the question. So we are trying to find C1 and C2. Those are unknowns, so we don't know if they exist or not. So we need to solve this system. So it's C1 times U plus C2 times V equal W. So we are trying to solve this non-homogeneous system. If the system has a solution, then we have C1 and C2. Then W is a linear combination of U and V. If this non-homogeneous system does not have a solution, so if there is a contradiction somewhere, then W is not a linear combination of U and V. So what do? Well, we write our non-homogeneous system. So basically we have matrix form like this. And we will form our augmented matrix form and apply Gauss-Jordan and elementary row operations. So something like this. Then we apply elementary row operations. And we get, after two operations, we get something like this. And then we see, I have a row of zeros and on the other side is not zero. So this means there's a contradiction in the system. So this system does not have a solution. So if the system does not have a solution, the constants, so scalars C1 and C2 do not exist. So they don't exist. So I cannot write this, it's impossible. Because the constants do not exist. There's a contradiction in the system. No solution. So, conclusion, the vector W that was given is not a linear combination of vectors U and V. Very simple. Why? Because I cannot find C1 and C2. So this is what I needed to solve. So on my augmented system, I apply elementary row operations and Gauss-Jordan. And somewhere in the process, I got a row of zeros, and on the other side of the bar, I got something different from zero. So this means there is a contradiction, so system does not have a solution, therefore constants C1 and C2 do not exist. Therefore, vector W is not a linear combination of U and V. Very simple. If the solution doesn't exist, W is not a linear combination of U and V. Another example. Another W and another U and V. The same process. We need to find constants C1 and C2 such that this equation is true. Can we find them? So we need to solve for our unknown C1 and C2, our non-homogeneous system. Again, we form non-homogeneous system under the form AX equal B. So this is it. Our unknowns are C1 and C2. Form augmented matrix. Apply elementary row operations and Gauss-Jordan. Oops, and we reach reduced echelon form here. So from here, we see that we have a solution. C1 is 1 and C2 is 2. So we have a unique solution in this case. C1 is 1 and C2 is 2. It was clear from this situation here. Okay. So C1 and C2 do exist. C1 is 1 and C2 is 2. And W is linear combination of U and V this way. So 1 times U plus 2 times V is equal to W. Therefore, W is a linear combination of vectors U and V. Because we have a solution, we found C1 and C2. It's very simple. We are solving non-homogeneous system. If the system has a solution, then vector W is a linear combination of U and V. If the system does not have a solution, then W is not a linear combination of U and V. Very simple. Again, another problem with different vectors U, V, and W. Again, we form a matrix system. So system of the form Ax equal B, non-homogeneous with unknowns C1 and C2, form augmented matrix form, use Gauss-Jordan and elementary row operations to solve. And what we see, we get something like this. But that's great. Now we solve for unknown C1 and C2, and we suddenly realize that we have infinitely many solutions, and the solution is of the form given here, where C2 is a free variable. So we actually have infinitely many solutions in this case. Well, that's good. If we have at least one solution, that's already good. That means that W is a linear combination of U and V. Some examples of coefficients, C1 and C2, for instance, I can say 3 times U plus 0 times V is equal to W. So that's one of the possible solutions. 1 and 1, that means U plus V is equal to W. Here minus 3, 3, which means minus 3 times U plus 3 times V is equal to W. Another example of the solution, 11 minus 4. So 11 times U minus 4 times V equal W. And last one here. So I change values for C and I get each time a different solution. In this case, I have infinitely many of them. As soon as I have one, I know that W is a linear combination of vectors U and V. In this specific case, we can write W in infinitely many ways as linear combination of U and V with this specific formula here. Another example, here I have 4 vectors with 3 components, so W is here. Is W a linear combination of U, V, and Z? Well, I need to solve this non-homogeneous system. This time I'm looking for constants C1, C2, and C3. Do they exist, yes or no? So I need to try to solve this non-homogeneous system. Here it is, system of the form X equal B, form the system, augmented matrix form. So again, apply Gauss-Jordan and elementary row operations. Once I'm done, I get one unique solution, 1 minus 1, 2. Therefore, solution exists, so my constants exist. So W is actually a linear combination of vectors U, V, and Z. And here there's an error. It should be U minus V plus 2Z equal W, as here. So W is a linear combination of vectors U, V, and Z. Here it needs to be 2 times Z. So in this case, we were able to find a solution. Therefore, W is a linear combination of vectors U, V, Z. In this question, we have 3 vectors, so W, and all of them have 4 components, obviously. So the question is W with 4 components linear combination of U and V, also with 4 components? So we are looking for scalars C1 and C2. Do they exist? Do they exist in such a way that C1 times U plus C2 times V is equal to W? Again, we form a system. In this case, unknowns are C1 and C2. So we have a non-homogeneous system Ax equal B. This is it. So we write augmented matrix form, apply Gauss-Jordan and elementary row operations as usual. And after applying all these operations, so I have this, and then I apply an operation on row 3. Here's what I get: a row of zeros with 1 on the other side. Notice here I have row of zeros and then 0 on the other side. That's fine. There's no problem there. The problem is here. I have row of zeros and 1 on the other side of the bar. That means there's a contradiction in the system. If there's a contradiction in the system doesn't have a solution. Therefore, C1 and C2 do not exist. Therefore, W is not a linear combination of U and V. So whenever the solution doesn't exist, W is not a linear combination of vectors U and V. Another one, again, 3 vectors. Question is always, is W a linear combination of vectors U and V? Again, we need to solve a non-homogeneous system. We are looking for C1 and C2 in this case. We form a matrix system, Ax equal B, non-homogeneous system. Write it in the augmented matrix form, apply Gauss-Jordan and elementary row operations, and we get this here. This is reduced echelon form. So we see that we have a solution. In this case, solution is -3/2 and 1/2. Therefore, C1 and C2 exist. Therefore, W is a linear combination of U and V. So that's it. W is -3/2 times U plus 1/2 times V. So W is a linear combination of U and V. So that's how we proceed when we need to find out if a given vector is a linear combination of other vectors. So basically we need to solve a linear system of the form Ax equal B. So this is non-homogeneous linear system. If this system has a solution, then our vector W is a linear combination of vectors U, V, Z, or whatever we are given. If the non-homogeneous system has a contradiction in itself, then there is no solution. Therefore, W is not a linear combination. So it's very simple. It all depends on the fact that we do have or do not have a solution for non-homogeneous system. You need to practice a little bit, solve some problems from the book. These are the problems that are related to linear combinations in chapter 3. So the book with the white cover, these are the problem numbers, and book with the yellow cover, these are the problems related to linear combinations. So please go and practice a little bit. It's not complicated. Another concept that we need to see, and this is very important, is concept of linear dependence and linear independence of vectors. Again, these concepts of linear dependence and independence can be applied to vectors, to matrices, to different types of functions. But for us, we are going to focus only on vectors in Rn, so columns of real numbers. And this corresponds to the section 4.3 in the book. So for us, we are only focusing on vectors. We start with a definition, and the definition itself will give us a way to find if vectors are dependent or independent. So we have a set of vectors here in Rn, let's say v1, v2, vr, and we have this homogeneous equation here. So constant times first vector plus a constant times the other vector plus a constant times the last vector equal to vector 0. Okay? So we know that this is a homogeneous linear system. As usual, a homogeneous linear system has always at least one solution, which is k10, k20, k30, kr0. So 0 solution is always a solution for homogeneous system. We know that. And it's called usually trivial solution. So now the only question is that the only solution for the system, or we have infinitely many of them? So when we have only a trivial solution, then the set of vectors S is called linearly independent set. Or we can say that vectors v1, v2, vr are linearly independent. If the homogeneous system here has infinitely many solutions, including the 0 solution, then we say that the set S is linearly dependent. Also, we say that vectors v1, v2, vr are linearly dependent vectors. So the definition here tells us actually how we can discriminate between vectors that are linearly dependent and independent. We need to solve a homogeneous system actually, but more specifically, all we need to see is how many solutions this homogeneous system has. If it has only one solution, the trivial solution, 0 solution, then the vectors are linearly independent. If the homogeneous system has infinitely many solutions, then the vectors are linearly dependent. So that's all it is. We have a bunch of vectors, and we need to see if the homogeneous system with those vectors in columns actually of the matrix has one solution or infinitely many. That's all. So the question that will be asked is, given a set of vectors v1, v2, vk in Rn, are these vectors linearly independent, or is the set of vectors linearly independent or linearly dependent? So we can ask about the set of vectors, is it dependent or independent? Or we can just say, are the vectors v1, v2, vk linearly dependent or independent? So that's the same question. From the definition, we can translate this into something workable, and the definition says that basically the question is, does the homogeneous system given here, so Ax equals 0, does it have a unique solution, in which case vectors are linearly independent, or the homogeneous system has infinitely many solutions, in which case the vectors are linearly dependent? So that's all we need to know. Forming a linear system, Ax equals 0, homogeneous system, we need to know how many solutions we have. If we have only one solution, then the vectors are independent. If we have infinitely many solutions, then the vectors are dependent. That's all it is, nothing else. So that's our strategy. To find out if a set of vectors in Rn is linearly dependent or independent, we need to try to see how many solutions homogeneous system X equals 0 has. If we have exactly one solution, trivial solution, unique solution, then the vectors are linearly independent. If we have infinitely many solutions for our homogeneous system, the vectors are linearly dependent. So the vectors are the vectors, column vectors with n components inside, n entries. Matrix A, so matrix here, is just matrix composed of the vectors. Each vector is put in a column. And our unknowns are C1, C2, Ck. So unknowns from here. And on the other side, we have vector 0 with n entries, obviously. So the only question is how many solutions our homogeneous system has. One or infinitely many. That's all. So simple cases, we have again bases for the R2. So vectors E1 and E2, 1, 0, 0, 1. They are obviously linearly independent because the homogeneous system given here, so the system here, has only one solution, C10, C20. So this is unique solution. Since it is unique solution, then vectors E1 and E2 are linearly independent. Now we notice that we have homogeneous system, and in this case we have a square matrix 2 by 2. We could also compute the determinant of that matrix because we know from our properties that we learned very well, when the determinant of a matrix is different from 0, matrix is invertible. That means that this system here, homogeneous system, has one unique solution, x equals 0. Therefore, the column vectors are linearly independent. So it's very useful to learn all those properties. In the case of here 3 vectors in R2, so all 3 of them have 2 components. By definition, we are solving this homogeneous system, so we are looking for C1, C2, C3. So this is our homogeneous system. We notice that we have 2 equations and 3 unknowns. And from our properties, a homogeneous system that has more unknowns, here 3, than equations, here 2, we know automatically that that homogeneous system has infinitely many solutions. So learning properties helps us. We know that this system will have infinitely many solutions. Indeed, we will have a free variable. Therefore, vectors v1, v2, v3 are linearly dependent because this homogeneous system has infinitely many solutions by definition. Obviously, if we don't know the properties, we can always solve and find out that we have infinitely many solutions because we have a free variable. Then we will conclude that vectors v1, v2, v3 are linearly dependent because the system, homogeneous system, has infinitely many solutions. So learning properties helps a lot. We don't need to solve, we just need to invoke the property, like we did here. In the case of R3, we have again our standard basis, E1, E2, E3. And these basis vectors are obviously linearly independent because again a homogeneous system here given here has one unique solution. Again, since this is a square matrix, we can compute the determinant, which is 1 in this case. So it's different from 0, which means matrix is invertible, which means homogeneous system Ax equals 0 has one unique solution, which means the vectors E1, E2, E3 are linearly independent. It all comes from the definition. So what happens if I have 4 vectors from R3? So 4 vectors with 3 components each. I need to solve this homogeneous system here. So we have v1, v2, v3, v4. So we have c1, c2, c3, c4. So we have 4 unknowns. When we form a linear system, homogeneous system, we see that we have 3 equations and 4 unknowns. So again, we have more unknowns than equations. And this is a homogeneous system. From our properties, we know that homogeneous system that has more unknowns than equations has infinitely many solutions, automatically. Therefore, vectors v1, v2, v3, v4 are linearly dependent. If we don't know the property, well, we can always solve. Once we solve the system, we will find that we have a free variable. Therefore, the system will have infinitely many solutions. Therefore, the vectors v1, v2, v3, v4 are linearly dependent. So we reach the same conclusion both ways. Which way you choose, your choice, depending on your knowledge. Some special cases where it is easy to tell if vector is or vectors are linearly dependent or independent. A curiosity, if I have only one vector, let's say v with n components, is that vector linearly dependent or independent? Very weird question. Well, if the vector is 0, so the set containing just the vector 0, that set or that vector is linearly dependent. The vector 0 is linearly dependent always, always. Indeed, I can multiply 0 by any number and still get 0. Because this is a homogeneous equation that I need to solve by definition. It's just special because I have only one vector. So I have one constant. So what are possible values of k such that this equation is true? Well, I can take k equals 7, minus 11, 55, 0 also. So I have infinitely many solutions for this equation here. Therefore, vector 0 is linearly dependent vector. If a vector is not 0, then that non-zero vector is always linearly independent. Indeed, to solve this homogeneous equation, the only way is to put k equals 0. No other choice, because v is non-zero vector. So if you have vector 1, 1, v is 1, 1, the only way to get k times 1, 1 equal to 0, 0 is to put k equals 0, obviously. So any non-zero vector is always linearly independent. Vector 0 on its own is always dependent. If I have two vectors, w and v, well, if one of them is 0, then the set 0w or 0v is linearly dependent. So whenever set has a vector 0, it is always dependent. And in general, whenever a set has dependent vector, the set becomes dependent. So 0 is dependent vector. So if I put another vector with 0, well, that set becomes automatically dependent. So if both vectors are non-zero vectors, so at least one component in each is different from 0, then the set VW is linearly dependent if and only if v and w are scalar multiple of each other. For instance, vector 1, 1 and 2, 2, they are scalar multiple of each other and they are linearly dependent. And the vectors are independent if and only if they are not scalar multiple of each other. For instance, vector 1, 1 and 2, 7. Okay, v1, 1, w2, 7. They are independent. I cannot multiply 1, 1 by one single number to get 2, 7. Right? So they are not scalar multiple of each other. So they are independent. So for two vectors, it's very easy. If they are scalar multiple of each other, they are dependent. If they are not scalar multiple of each other, they are independent. So any set containing vector 0 is automatically dependent. An example here, so I have 4 vectors, one of them is 0, and by definition, I'm looking for C1, C2, C3, C4 that satisfy this homogeneous equation. The only question is, do I have only one solution for C1, C2, C3, C4, or I have infinitely many? Well, I have infinitely many. All I need to do is set C2, C3, C4 at 0. Okay, so this becomes 0, and then C1 can be any real number I like. So I have infinitely many of them, so this homogeneous system has infinitely many solutions. Therefore, the set here containing 0, u, v, and w is linearly dependent. So 0 in any set makes the set linearly dependent. Some examples of possible options. You see, I put 0 at C2, C3, C4, and I just change the value of C1, and I have infinitely many choices. So this homogeneous system will have infinitely many solutions. Therefore, the set here is linearly dependent. So 0 makes any set linearly dependent. Another interesting result is when I have a set of vectors, that set is linearly dependent if and only if at least one of the vectors in the set is linear combination of other vectors from the set. For instance, I have u, v, and w, and for some reason w is 3 times u minus 2 times v. So w is a linear combination of u and v. Then the set u, v, w is linearly dependent. As soon as one of the vectors is linear combination of others, bye-bye, the set is dependent. Another example, u is minus 4 times v, so u is a linear combination of v, of one guy, so this is minus 4v plus 0w, if you wish. So u is linear combination of v and w. Therefore, the set here u, v, w is linearly dependent. And obviously set is linearly independent when no vector is linear combination of others. So those are results that can simplify our process. We don't need to solve, we just need to observe when it is possible. It's not always obvious what to do, then we just solve. Another interesting result, if I have a set of R vectors in Rn, so let's say n is 3, so I have certain number of vectors in R3. So if R is greater than n, so let's say R is 7 and n is 3, then the set is linearly dependent. If R is 4 and n is 3, set is again dependent. So if I have 3 vectors with 2 components, the set is dependent. They are dependent. If I have 4 vectors with 2 components, they are dependent. If I have 4 vectors with 3 components, they are dependent. If I have 7 vectors with 3 components, they are dependent. If I have 5 vectors with 4 components, the set is dependent. So each time I have more vectors than each vector has components, the set is automatically dependent. Now, unfortunately, when we have, let's say, 4 vectors with 4 components, we don't know what's going on. We need to solve the homogeneous system and see how many solutions we have. 1 or infinitely many. The same thing when we have, let's say, 3 vectors with 7 components. We don't know what's going on. We need to solve the homogeneous system and see how many solutions we have. But what is interesting is if I have 7 vectors with 6 components, I know immediately that they are linearly dependent. If I have 6 vectors with 4 components, I also know they are dependent. As soon as I have more vectors than each vector has components, the system is the set is dependent. This is obvious because you will end up with a system that has more unknowns than equations. And we know that homogeneous system that has more unknowns than equations has infinitely many solutions. Therefore, the set will be dependent. A result that can be used when we have n vectors with n components, so 2 vectors with 2 components, 3 vectors with 3 components, 4 vectors with 4 components, 7 vectors with 7 components. So we can proceed normally, trying to solve homogeneous system, or we can try to compute determinant. So this set of n vectors from Rn is linearly dependent if and only if determinant of a matrix is 0. So we put each vector as a column, one column of the matrix, and we compute determinant of the matrix. If determinant is 0, vectors v1, 2, v2, v3, vn are linearly dependent. If determinant is different from 0, then the vectors are linearly independent. Which is normal. We know that from properties, since this is a square system, that's why we can compute determinant of the matrix. Homogeneous system with square matrix, when the matrix is invertible, which means when determinant is different from 0, Ax equals 0 has one unique solution. Therefore, the column vectors v1, v2, vn are linearly independent. when the determinant of a square matrix is 0, then the homogeneous system Ax equals 0 has infinitely many solutions. Therefore, vectors v1, v2, vn are linearly dependent. So this comes from the properties straight. So who learned the properties is blessed here. So here, an example, we have three vectors, u, v, w, and we can see easily then w is actually negative 2 times v. So we know immediately that that v and w are linearly dependent. So the set vw is linearly dependent. Vectors vw are linearly dependent. We see that w and u, they are not scalar multiple of each other, therefore wu is linearly independent. So vectors w and u are linearly independent because they are not scalar multiple of each other. Same reason for v and u. They are independent because they are not scalar multiple of each other. Now, the set with u, v, and w is linearly dependent. Why? Well, because we already know that v and w are dependent. Therefore, the set containing v and w will still be dependent. So question, given three vectors u, v, w, find out if they are linearly dependent or linearly independent. So what we need to do, we need to form homogeneous system by definition. Here it is. And find out how many solutions the system has. Does it have exactly one solution? 0. Or it has infinitely many. Now, our normal procedure would be just to solve the homogeneous system and see how many solutions it has. Since this system is square 3 by 3, we can also opt for computation of determinant and see if the determinant of A is 0 or is not 0. We can choose one or the other of the options. Both of them are correct, since we have a square matrix here. So if we choose to proceed by Gauss-Jordan, so we are just solving the homogeneous system while we apply elementary row operations, Gauss-Jordan, and in this case we reach a reduced echelon form identity, and the only solution is 0. So this system, homogeneous system, has one unique solution, 0, therefore vectors u, v, w are linearly independent. One interesting thing, when we apply elementary row operations, we reach echelon form in our process. So already from our echelon form, we can know how many solutions our system, homogeneous system, has. From the echelon form, we see from the last equation that C3 is 0. So we bring it here, we will have C2 0, we bring C3 and C2 0, we get C1 0. Like using back substitution if you wish. But also you see that this matrix is triangular and diagonal entries are different from 0. So you already know that the determinant of this matrix is different from 0. So this system will have unique solution. So our original system will have unique solution, which is 0 solution. C1 0, C2 0, C3 0. Therefore, since this is the only solution, vectors u, v, w are linearly independent. So we can conclude already from echelon form. We don't need to push for the reduced echelon form. If someone likes to compute determinant, since we have a square matrix, it's fine. Here determinant is non-zero, therefore matrix is invertible, therefore homogeneous system with the invertible matrix has one unique solution, x equals 0. And again, that means that u, v, w are linearly independent. Remember, all we need to know is how many solutions our homogeneous system has. One or infinitely many. That's all we need. Another example, another three vectors from R3. Again, we want to know how many solutions our homogeneous system has. Again, since this is a 3 by 3 system, we can either solve using Gauss-Jordan or compute determinant, our choice. Whichever strategy we choose, it's fine. If we choose Gauss-Jordan, we do the linear elementary row operations, and we get reduced echelon form here. So you see you have a row of zeros here, which means that this system here has actually 2 equations and 3 unknowns. So you have a homogeneous system with 2 equations and 3 unknowns. So homogeneous system that has more unknowns than equations, which means this system will have infinitely many solutions. Learning properties is very important. So we can even write the general solution of this form, and one variable C3 is a free variable. Therefore, we have infinitely many solutions. Therefore, vectors u, v, w that form columns of the original matrix, they are dependent because we have infinitely many solutions for homogeneous system. Obviously, we could have stopped already when we reached echelon form because we got here row of zeros, and this transformed our square system actually into a system of 2 equations with 3 unknowns. And we again know a homogeneous system that has more unknowns than equations has infinitely many solutions. Therefore, vectors u, v, w are linearly dependent. If someone wanted to compute the determinant of A, well, after computation you find the determinant is 0, which means that matrix is not invertible. Therefore, our homogeneous system with square matrix that is not invertible has infinitely many solutions. Therefore, vectors u, v, w are linearly independent. So you have several ways to find the conclusion. Whichever way you choose, it's okay. You just need to justify what you're doing. Specify clearly right. Here we have 4 vectors with 3 components. Oh, are they linearly dependent or independent? Well, we saw a result telling us when we have 4 vectors with 3 components, they are automatically linearly dependent. So we need to solve homogeneous system with unknowns C1, C2, C3, C4, and we need to figure out how many solutions. So either you know the theory and then it's easy, or you don't and then you solve and you figure out stuff. So again, we have 4 vectors from R3. Therefore, vectors are linearly dependent. Why? Because homogeneous system that is written here has 3 equations and 4 unknowns. So the homogeneous system has more unknowns than equations. We automatically know that there will be at least one free variable. Therefore, this system has infinitely many solutions. That's what our theory says. Therefore, vectors u, v, w, and z are linearly dependent. Learn the theory, relearn the results, and you will work less. So all you need to do is write the system and tell me that you have more unknowns than equations, and a homogeneous system with no more unknowns than an equation has infinitely many solutions. Therefore, the vectors u, v, w, z are linearly dependent. Very easy. In this example, we have 3 vectors with 4 components each. Oh, so now we don't know what's going on. Definitely not. So we need to solve a homogeneous system. So ax equals 0, and 0 has 4 components because each vector here has 4 components. Our unknowns are c1, c2, and c3. So the question is how many solutions the system has. In this case, we need to try to solve. There's no other choice. The system is 4 by 3, therefore matrix is not square. So we cannot use determinant, definitely not. We must try to solve using Gauss-Jordan and elementary row operations. So we do that, and our reduced echelon form is here, and we figure out that the only solution is, there's only one solution, which is 0. Therefore, u, v, and w are linearly independent vectors. Obviously, in our process, we could stop also once we reach echelon form, because from this echelon form, okay, I have one row of zeros, but that doesn't mean much here because I still have 3 equations with 3 unknowns. So from this echelon form, I can see from the equation number 3 that C3 is 0. Bringing it back by back substitution, I can figure out that C2 is 0, and doing the same on the first equation, I figure out that C1 is 0. Therefore, this system has one unique solution, which is 0. Also, you see here you have a 3 by 3 matrix, and the main diagonal has 1, 1, 1. So the determinant of this small matrix here is 1. So that's another trick. Since we have one unique solution, the vectors are linearly independent. Another example, 3 vectors with 3 components. Are they linearly dependent or independent? Well, we form homogeneous system and we figure out. This time we can just compute determinant or use Gauss-Jordan again, it's fine. In this case, determinant happens to be 0. That means that my matrix A is not invertible. So I have a homogeneous system with square matrix that is not invertible. From the theory, I know that this system has infinitely many solutions. Therefore, vectors u, v, and w are linearly dependent. Obviously, if you try to use Gauss-Jordan and elementary row operations, because for some reason you don't want to compute the determinant, which is totally fine, we end up with this echelon form, or actually reduced echelon form. We have a row of zeros, fine, and then we have this reduced echelon form here. From here, we find the solution, so we are looking for C1, C2, C3. We have a solution of this type, so this is the general form of a solution with one free variable. Therefore, we have infinitely many solutions. Therefore, vectors u, v, w are linearly dependent. So same conclusion as if we used the determinant. Obviously, it will always be the same conclusion. Another example here, I have 4 vectors with 4 components. So I need to see if they are linearly dependent or independent. I have 2 options because I have now system 4 by 4. I can use Gauss-Jordan or compute the determinant. My choice, whichever one I choose, it's fine. I will reach the same conclusion. So in this case, after computation of the determinant, that took half an hour, we figured out the determinant is different from 0. So I have a homogeneous system with invertible matrix. From theory, I know that this system has one unique solution, x equals 0. Therefore, vectors u, v, w, and z are linearly independent. So in summary, if we are interested in finding out if a set of vectors is linearly dependent or linearly independent, most of the time we will need to solve a homogeneous linear system and find out how many solutions that system has, 1 or infinitely many. If the homogeneous system has only one solution, then the vectors are linearly independent. If the homogeneous system has infinitely many solutions, then the vectors are linearly dependent. Here are some exercises from chapter 4, section 3, that deal with linear dependence and independence. So in summary, we have seen 2 very important concepts that we are going to use a lot. Concept of linear combination, and to figure out if a vector w is a linear combination of vectors v1, v2, vk, so all of these are given, w is given, v1, v2, vk are given, so we want to know if w is linear combination of v1, v2, vk. We need to solve non-homogeneous system of the form Ax equal b. If the system has a solution, one or infinitely many, then W is a linear combination of V1, V2, Vk. If this non-homogeneous system, does not have a solution because there is a contradiction somewhere, then W is not a linear combination of V1, V2, Vk. Very simple. And in the case of linear dependence and independence of a set of vectors, we need to solve a homogeneous system, Ax equals 0, and figure out how many solutions the system has. If the system has one unique solution, x equals 0, then the vectors are linearly independent. If the homogeneous system has infinitely many solutions, then the vectors are linearly dependent. So that's the summary of the material that we need to learn and absorb, because we are going to use these expressions very, very, very often.